This is an introduction to quantum computing. My name is Larry Leibovich. I'm an adjunct senior research scholar at Columbia University, and I study complex systems and also data science. The quantum computers could be much more powerful and much faster in applications like these. We know that in natural language processing, what we've been doing for a long time is an edict from a British linguist who said, "You shall know the meanings of words by the company they keep." And all of NLP is based on the association of words, but not their meanings or even deeper things like irony and context. And having much more powerful quantum computers might allow us to do that. In terms of computational chemistry, that would help us solve the 3D structure and motions in large natural molecules to help design molecules and drugs. In cybersecurity, quantum mechanics, quantum computers can provide much stronger cryptography and the opposite of that, cryptoanalysis of breaking codes. In finance, the additional power would help maximize portfolio returns and compute risk under different complicated market scenarios. And in enterprise operations, maximizing supply chain, prediction, and creating new types of databases, machine learning, and artificial intelligence. So there are different worlds. In the everyday world we live in, we're used to big things and forces and motions like gravity and heat. And these forces and motions are deterministic, and we can measure and predict them with certainty. But at the very, very smallest sizes of things, where quantum mechanics lives, in light and photons and atoms and even transistors in your laptop, it doesn't work like that. All we get are probabilities, and we can determine those probabilities with great accuracy, but it's just probabilities. And when you measure something, you also change it forever. In the quantum world, quantum computers could be more powerful because of superposition. That is, a quantum entity can be at many different states at the same time until you measure it and then you only find one thing. And we can predict exactly the probability of finding each state, but we can never predict exactly which state we will find. This provides a quantum advantage, that a single operation works on all those combinations of states at once, so it does many different things. The second thing quantum allows us to do is called entanglement. That is, something here is actually in some odd way connected to something else over there. And that means that, again, a single operation can work on many different things at once. What's been called quantum supremacy means that in certain computations, a quantum computer could be 10 to the 28th times faster than current computers. And here I've written out all the zeros for 10 to the 28. But the challenge of quantum computing is, first of all, the hardware. Quantum properties dissipate when you connect this small quantum world with our big physics world. So we have this design paradox. Quantum computer must be both isolated from our big world to retain its quantum properties, but equally connected to our world so we can input data, control the computation, and read the output. The second challenge is software. Programming quantum is very different than conventional computers, which maybe have gates like OR and 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 XOR and plus and multiplication. Quantum gates are entirely different and work in a different way. The irony here is that most of our data science tools are really based on linear algebra. And quantum is also linear algebra, but it's a different kind of linear algebra called a Hilbert space. So anything that has a small energy difference, anything, lives in the world of quantum, and we can use that as the basis for a quantum computer. And this includes things like small bits of electricity or magnetism, single atoms, or where the electrons are in those atoms, what are called dots of atoms, small groups of atoms, a wrong atom sitting in a place in a crystal to create a different energy level, light, that is photons with spin up or spin down, even the positions of things or the shapes of boundaries if they lead to this small energy difference. So these are some examples of that. People in several different quantum computers have made integrated chips because this is a mature technology, and it's an oscillator, an RLC oscillator, and it has different energy levels that can be used to create a quantum computer. Or we can have isolated atoms like a calcium atom and change the energy level of an electron. We can have topological qubits where either the shape or how many holes something has in it changes different energy levels, or in photonic devices where we have light moving through the system and the light can have spin up or spin down for each photon. So this is what quantum mechanics looks like. We have a wave function that tells us we have a state 0 and a state 1. And these prefactors here tell us what combination of those states we have. So this is that superposition, that this wave function contains both the state 0 and the state 1 at the same time. And we have this Born rule that says the square of this first number tells us the fraction of times we'll observe it in state 0, and the square of this, the fraction of times we'll observe it in state 1. So this is what the mathematics looks like. State 0 is a vector with two possible values in the vector. So a 0 is 1, 0, and a 1 is 0, 1. And we're going to use matrix operations. So we multiply a row times a column to get the new row, and a row times a column to get the new row. And this is an example of a quantum operator, this matrix. When we multiply this matrix on the 0 operator, we get 1. And we multiply that matrix on the 1 operator, we get a 0. So this is really a NOT operator. It changes a 0 to a 1 or a 1 to a 0. More complex operator here is called a Hadamard operator. Here, when we operate on a 0, we make a combination now of both the 1, 0 and the 0, 1 state. And again, the square of this is how often when we measure something we'll find this state and how often we'll find that state. So the Hadamard operator has turned a 0 into something that's 0 half the time and 1 half the time. And in fact, if we do a Hadamard on a 1, we actually get a very similar result too. So those can both be used in what's called quantum key distribution, which is a secure way to send a key to use in other encryption systems later. So one of the odd things of quantum mechanics is the no cloning theorem. We cannot make a complete copy of a quantum state. If we're dealing with a conventional computer with bits, it's easy to make a copy. We make an assignment. But we can't do this in qubits because once you measure something, you change it forever. So if we're sending what will be a number that corresponds to a cryptographic key, if no one is listening, we receive the same number. But if someone is trying to do a man-in-the-middle attack, if they read the numbers that are being sent and then try to just resend them to fool us, in fact, it doesn't work because their act of measuring the numbers forever changes them, and there are ways then of detecting that change. That's called the BB84 protocol. And in fact, there are these quantum key distribution networks. This is commercially available, off-the-shelf hardware. And they've been set up in the US, the EU, Switzerland, China, Japan, and actually many other locations. So what can we do with 2 qubits? So if we have these 2 qubits, 0 and 0, we can combine them to make a double 0. When we do that, the way they combine is by what's called a tensor product, so which is illustrated here. And what we wind up with, although we started with a two-dimensional system, we now have a 1, 2, 3, 4-dimensional system. When we combine n bits in a computer, the dimensionality of what we get is 2 times n. But for n qubits, the dimension we get is 2 raised to the n. And part of the power of quantum computing results from this higher dimensional increase as we combine qubits together. We can create a whole series of operations operating on our 0, 0 qubit. If we do that, what we wind up is 0, 0, and 1, 1. And again, squaring this, we see that half of the time we'll wind up with a 0, 0, and the other half of the time we'll wind up with a 1, 1. Now, each of these qubits is a physical entity. We could take one of them and leave them here on the Earth and move the other one, that second 0, up to the moon. But every time we measure a 0 on the Earth, we'll measure a 0 on the moon. And every time we measure a 1 on the Earth, we'll measure a 1 on the moon. Remember, each time there's only a 50% chance of getting one of these things or the other. But we never get a 0, 1. So how can this happen? How are they connected? One of the people who was most upset about this was Albert Einstein. And he called this spooky action at a distance. We usually refer to this now as entanglement. And this is an example of that. This is a run on an IBM quantum computer. Here it's being programmed by a graphical interface, and it's run 1K times. You can see about half the time we get a 0, 0 for the 2 qubits. The other half of the time we get a 1, 1. Only infrequently do we get 0, 1, and 1, 0. We shouldn't be getting this at all. But again, this quantum computer hardware is not perfect. There's that little bit of dissipation, and so we get some things where it really shouldn't be getting in this real quantum computer, in this case that had 5 qubits. A few years ago, a Chinese satellite used entanglement to send photons to 2 different ground stations that were nearly 1,000 miles apart. And every time one station reads a 0, the other reads a 1. And again, when one reads a 1, the other reads a 0. And once again, we can't predict where they're going to get a 0 and 1, but somehow, by spooky action at distance, they communicate together, so we never get a 1, 1 or a 0, 0. In the public key encryption system, Alice picks numbers P and Q, multiplies them together to create N. She does other things on those to create a public key and a private key. She keeps the private key to herself, but she sends the public key to Bob. And Bob uses that public key to code his message, which goes back to Alice. And Alice has that D, which you need to decode the message. Only Alice can read it because only she has her private key. But whoever can factor N into P and Q, because you see she's included that N with the E she sent, can compute that private key and also reads Bob's message. But it's not so easy to do that factoring. For a current version of RSA using 2K bits, a classical computer would take 10 to the 38th operations to factor N into P and Q. But a quantum computer running Shor's algorithm would be able to do that in 10 to the 10th operations, or 10 to the 28th times faster. This is where that 10 to the 28th comes from. So Shor's algorithm is able to factor N into P and Q by using superposition, by creating a function of many values, and it does it all at the same time. So again, one operation creates many different things. It then uses entanglement to create a discrete Fourier transform to figure out the period in that set of numbers. And once you know that period, you can use things from number theory to factor N into P and Q. And in fact, this has been implemented on real quantum computers. It's been implemented on devices that use photonics or light. It's been implemented using computers that use calcium ions with an electron moving between different energies, and on superconducting oscillator qubits. Now, the amount of things they factored are relatively small numbers, 15 and 21, but these are relatively small quantum computers. And at least this is a proof of concept and presumably could be scaled up to factoring much larger numbers. Another aspect of quantum computers is a little bit different, called a quantum annealer. Here, there are no gates in the computers I showed you before, but there are qubits that are connected to each other, and the system finds its energy minimum. And you can do a lot of interesting things even with this, without the qubits. We know that neural networks have nodes that are connected by algebraic functions, like hyperbolic tangents or rectifying linear units, and they're usually feed-forward. But quantum Hopfield Ising networks are nodes connected by quantum functions, like in this machine. And it's been shown that some very hard NP problems can be formulated as these quantum Ising networks. But until recently, such quantum Ising networks could not be solved. But now they can, by a method called equilibrium propagation, which is analogous to backpropagation in neural networks. And so this approach shows promise in using quantum annealers in machine learning and artificial intelligence without the need to use quantum gates. And I've listed some references for the facts above them here. Now, even if quantum computing never comes to fruition, we've already created a quantum computer ecosystem where people have spent lots of money, created new chips and solid-state devices and photonics, and are creating new algorithms for machine learning and AI from a quantum standpoint. And the point that Marina Mazzucato has made about things like this in her book, The Entrepreneurial State, was the importance of the defense and the Cold War and the moon landing wasn't to go to the moon, but it was to create a whole series of technologies, as shown here, that opened up the doorway ultimately for much faster computers and iPhones and a whole bunch of new technology. In the same way, the research being done in quantum computing is creating a whole ecosystem of other things. So even if quantum computers never materialize, there will be lots of use of other quantum properties in a lot of things in our world. But if quantum computing does work, the power of quantum computation will be able to do many things, to deal with many high-dimensional problems in physics, chemistry, biology, psychology, sociology, to make much better predictions in terms of weather and designing metamaterials, in terms of computer to do natural language processing and machine learning and AI in much more powerful ways, in organizations to maximize logistics and social patterns of very complex systems, and in finance, make much better predictions about portfolio management and risk predictions. Thank you.